Now we're going to look at another example of hypothesis testing, this time in the context of comparing multiple distributions. And we'll introduce a new test statistic called the total variation distance. So in 2010, the American Civil Liberties Union, the ACLU, presented a report that was discussing jury selection in Alameda County in California. And the report concluded that there were certain racial and ethnic groups that were underrepresented among jury panels. We are going to take some of the data from the report and conduct a hypothesis test to see if our test can corroborate their conclusions. So just as we discussed in a previous jury example, the way jury selection works is you have all eligible jurors in a county that is randomly selected, or that is a list that you use for randomly selecting a jury panel, and then from that panel, it's whittled down to the final jury. In terms of the laws in California, it's supposed to be that all persons selected for jury service shall be selected at random, and they shall be a representative cross-section of the population. The data that the ACLU compiled was actually from a total of 11 felony trials during 2009 and 2010. And in those panels, the total number of people who reported for jury service on the jury panels was just under 1,500. They gathered demographic data on all of those jury panel members and then compared with the composition of all eligible jurors in the county. And so here's the data they compiled, and these are proportions of both eligible juror candidates and then the actual proportions of the panel members that identified with these different ethnicities. And so we can see that the eligible versus what actually showed up was different. In certain cases it was higher, certain cases it was lower. And so the question is this reasonable? Is this a reasonable amount of variation that we could expect given that this was a random sample? So would the composition of jury panels be a realistic outcome if the jury panel selection process was truly unbiased? And that's what we'd like to test. Okay, so our null, let me move this. Let's set up our null so that we say that the people on the jury panels were selected at random from the eligible population. So any difference in ethnicity that we see between the eligible population and the jury panel is just due to chance. Now, to be able to use this as a null, I need to be able to either simulate or mathematically calculate a model of probabilities under this null. And so really I need to think of what's a mathematical model. We can imagine randomly sampling, and we'll want to match the same number of people that the ACLU had in their analysis, so just under 1,500 people, randomly sampling from a distribution that looks like the eligible population, and see what type of proportions we could end up with. And so if you think back to models of random variables that this mimics, this can be modeled via a multinomial distribution. We would let n be 1,423, the number of jury panel members that they had in their report. And then the probabilities we'd be using for this multinomial is the eligible population demographics. Now, I'm going to put one little asterisk to this, because in using a multinomial, we're basically assuming that we are randomly sampling with replacement each time we sample a new prospective juror. And in theory, what they did in the actual jury selection was probably random sample or sampling without replacement. And it's okay for us to model this using replacement because the population is huge compared to the sample size. So us using a multinomial distribution, which is IID, is fine to model this situation where they likely sampled without replacement. All right, so then what we need to do next is model the distribution of a test statistic. So now we need to pick a test statistic. And that's going to depend on our alternative hypothesis. So here, my alternative is just to say, no, the selection of the jury panels was biased. I'm not going to indicate a direction here because you'll notice in some cases I see an increase, in other cases I see a decrease in what we would expect. So I won't necessarily choose, I can't say it's biased towards this or against this, we're just going to say it's biased. And I need to choose a significance level before I go further into this process. So for our purposes, again, common conventions is to use a 5% or a 1% cutoff. Let's use a 1% here. And again, this is completely up to the context of the situation and the data that you're working with, but 1% is reasonable as a cutoff. So now I need a test statistic that I can now model the distribution of the test statistic, assuming that the null hypothesis holds. So let's think about what would be a way that I could use the output from a multinomial to somehow come up with a statistic that will help me determine if these distributions are really very different, more different than we would expect just from chance. Okay, so one way you can think about it, these are the same distributions just plotted on a bar chart, is I want some way to measure the distance between these distributions. And so I want to say, like, how close are they? And there's lots of different categories here. I don't just have one category. So I need to think of somehow accumulating information about like how far away those are from one another, how far away those are, how far away those are, and somehow aggregating it all into one statistic. And so this is actually a well-known problem, and so there's actually a commonly used statistic to address this question, and it's called the total variation distance. So how do you calculate TVD? In general, for each category, you compute the difference in proportions between the two distributions. So here, if I look at each category and I'm just saying panels, or here I'm doing eligible minus, nope, I went the other way. And we'll see why the direction doesn't matter in a minute. But I did panels minus eligible to get 11%. Here there's a negative 10%. Here there's 0, etc. So that's how we start. And now I'm going to take the absolute value. And I'm going to point that out because if I didn't take the absolute value, if I just added up all the differences as they are here, you're going to notice you get 0. Because the total of all these proportions have to add 1, and so do the total of all of these proportions. And so if I take eligible or panels minus eligible or vice versa, I'm going to end up with 0 for my sum of the differences, right? So before I sum all of these to try to aggregate them, I'm going to take the absolute value. That's what I have here. Now I can sum these absolute differences, and that gives me a valid statistic. And so that's really close to what we use for TVD. You're welcome to just stop there. I mean, that's a totally valid statistic, is to take the sum of the absolute differences. By convention, we've actually taken that value and then divided it by 2 for the actual TVD statistic. This is just a mathematical convention. And it's basically highlighting the fact that if you were just to add the positive values here, right, they would add to 0.14. If you were just to add the negative values, they'd add to negative 0.14. So by taking the absolute value and then summing, I'm basically double counting that information, right? I'm not getting any new information out of it. So we divide by 2 basically just to say, what's really the difference in either the positive or the negative direction? Again, just a convention, you won't get a different answer if you don't divide by 2. You'll get a different statistic, but it won't affect the overall conclusion of your test. So this is just to let you see a commonly used statistic in which we do divide by 2. Oh, so let's actually calculate it for this. So you can see again that that is just going to give me 0.14. So that is the TBD for this particular data set compared to my particular panel composition compared to the eligible population composition. Now, what I need to do is actually simulate, because this in particular, this is called my observed test statistic. And we're going to use that in a minute. But in general, we actually need to simulate the entire distribution of possible test statistics that we could get. So let's go jump to the notebook to do that. So now we're going to pop over to the hypothesis testing notebook, and we're going to go down to example 2. So let's jump to here. And we're going to just actually create a data frame that has the data that the ACLU compiled. You can visualize it like I had shown in the slides. And again, our question is, are these differences between the red distribution and the blue distribution something that could have happened just by random chance due to the fact that the red distribution is just a random sample? Or is this not something that would have likely happened by chance? Is there some bias that's happening? So we're going to just make an array that has the proportions from the blue distribution. And then we're going to imagine just doing a random simulation. Here I'm just going to sample 1,423 jurors as they did in the report here, assuming that this was the underlying distribution of the population. And then I get this observed distribution. So and this is simulated here. So here's the eligible in blue, the panels that we saw in red, and then in orange is my simulation of like a possible outcome we could have gotten if I was randomly sampling with replacement proportionate to the blue distribution. And you can imagine doing this again and again, and we're just going to see how much the orange varies. And is it possible that the red that we see here could have happened? Would the orange ever line up pretty close to the red one that we actually saw just by chance? So here's a new one. Okay, this one's slightly different. Again, that's what we're going to try to simulate. And to summarize this is not a way that we can make a nice decision by doing this over and over. I need to summarize all of this using a test statistic, which will give me a single number. And so we just defined in the slides that we can use the total variation distance as our statistic. So these are the steps to grabbing the total variation distance. Is we take the difference in proportions, we take the absolute values of those, and then sum. If we did it the other way around, if you took the difference and then summed them, you'd end up with 0 every time. So here's the TVD of our observed data. That was our observed test statistic that we just calculated in the slides. And now I can do the TVD of one simulation. So one possible simulation round, I get a TVD of 0.01. I could do it again, I could do it again, and this is what I want to create a distribution of. What are possible TVD values I would see, given my assumed underlying eligible population distribution? So here I'm going to just run this. Let's do 100,000 times. And I'm going to plot our distribution. So this is our distribution of our test statistic, assuming the null hypothesis is true. Right? And these are possible values for total distance variation that we might get just due to the randomness in our sample. Now, I could even do more than 100,000 if you want. So let's do 1,000,000 here just to make it even. Again, not necessary, just showing you we can do that to make it even more precise. Okay, let's pop back to the slides now to see how we use this. So in the Jupyter Notebook, we simulated this distribution, and now we're going to add in our observed test statistic onto this distribution. That observed test statistic was 0.14, and we can see it is far, far, far in the tail of this distribution. If the null hypothesis was true, highly unlikely to observe what we did for our jury panels. So this is making us really have some pause and be suspicious about the fact that our null hypothesis doesn't look so reliable. Okay, so to actually quantify this, we're going to calculate the probability of observing a test statistic as extreme as 0.14 or more extreme. And by that I mean more in the direction of the alternative. So we're going to calculate the probability that the test statistic is greater than or equal to 0.14. And to do that, we're going to go back to the notebook and do this using our simulation. So that will be actually what's called the empirical p-value, because it's calculated using our simulation. So here's our visualization of our simulated distribution and then our actual observed test statistic. And now I want to calculate the empirical p-value. I'm calling it empirical because I'm using the simulation to get the p-value. So out of my array here of all my TVDs, I want to see how many of them are greater than or equal to 0.14 out of the total number that I did. And so n up here, let's see, we're going to put it back up. Yeah, we had n was 1,000,000. Yep, great. And so here I'm going to put that here, and then we're going to divide this one out by 1,000,000. And we see 0. 0 out of 1,000,000. So we know for sure, again, your p-value and the theoretical p-value will never be exactly 0. We just know right now it's less than 1 in 1,000,000. So it's definitely less than 1 in 100. It's definitely less than our significance cutoff of 0.01. So that is going to tell us, based on this, that we reject the null. Our data is consistent with the alternative, that the jury panel was not representative of a random selection from the eligible population. So this does support the ACLU's conclusion that the panels were not representative, but it doesn't say why. And so we're going to talk a little bit more about that on the slides, but I will point out that there's a lot more information at the link in the textbook. So now just to summarize what we showed in the Jupyter Notebook, since our p-value is less than our significance level of 0.01, we reject the null. And so this says that our data is more consistent with the alternative hypothesis, and we say that this result is highly statistically significant. Now let's talk about this in a little more detail in terms of the actual context. So this does tell us that our results support the ACLU's conclusion that the jury panels were not representative of the distribution provided for the eligible jurors. But it doesn't tell us why. And this is where, as data scientists, we need to be very careful as well as cognizant of all the factors that affected this result. So the ACLU went into a much deeper investigation into this, and there were some factors that they found that likely led to this discrepancy. The first is that the county wasn't actually using a very great random sampling software. And so it's quite possible that when they were trying to do a random sample from eligible jurors, it really wasn't so random. The second is that their sampling frame consisted of people who were registered with the DMV or registered voters. And so that eliminates people that they can't reach due to out-of-date addresses, or people who are not registered with the DMV or a registered voter. You might still have eligible jurors that don't fit that description. And then there's the problem that even when they do reach, or they do have someone on their list to actually put them in the jury panel, those panelists have to be able to appear. And it's not necessarily feasible for everyone because employers are not actually required to provide compensation for jury duty, and some employers don't. And that leads to some people not actually appearing when they are summoned to a jury panel. The other piece I want to point out here is we didn't talk about how they got the data. And that's a very important piece to consider when you're making conclusions based on data. So the ACLU had to somehow estimate the demographic of all eligible jurors. And they reported that they used estimates that was developed by a professor from San Diego State, but they were based on 2000 census data from the year 2000. And again, they themselves were an estimate. So it's quite possible that there was some error. Not only because of the timing difference, the 2000 census versus 2010, but also just the fact that it was a model, it was an estimate that was developed by this professor. The other reason or other data quality issue we need to be careful about is we were using the estimates of the demographics for the actual jury panels, but the report didn't exactly explain how panelists were classified into their categories. And so it's possible that between this data set and this data set, there was not necessarily consistency in who got classified in what demographic, and that could have led to an incorrect conclusion. And then the other piece, which we've hinted at or we discussed on the previous slide, was there really is non-response bias, because the data that we received for the demographics of the jury panel assumed that the juror who was summoned actually showed up. So it is quite possible that a juror was summoned and didn't show up, and then it looked as if the jury panel had an not random or not representative selection, but that was more just due to this non-response bias from jurors who didn't come. So the ACLU did address some of these issues and gave some recommendations in their report, especially about following up with jurors that don't respond and trying to encourage compensation from employers and or the state for jury duty. So just to recap the steps that we went through in this process, here are the main steps in hypothesis testing. And we will be revisiting this as we continue to look at applications and different scenarios where we can apply this statistical tool.